right, we're now recording, and I hope you see the Chapter 6 Electricity um, first page, right?
Yes, sir.
Okay, good deal. Okay, I know Valerie's going to be late today. Her work schedule has messed her up this week. I know Gerald had, I think, the same problem earlier this week and last week, so welcome back, Gerald. Okay. Um, so while we're waiting for others to come in, I hate to repeat this several times, but I probably wind up, oh, here comes Amia. Let me get her marked present. All right. That gets us up to enough for a um, basketball team. Okay. Let me make sure there's nobody else waiting. Nope, 5 students so far. Okay. I'll probably repeat this many times over, but they really are pushing it now. I may have already said it once before, but some of you may not have been here, or I may have forgotten in this class, but let me say it again. Evidently, enrollment registration for spring term is way down. Now, I don't think this is probably all the students' fault. I think some culpability goes with the administration too, and here's why I say that. We just started this new system called Banner last summer, and last summer they were all over the place, getting people to go to the virtual advising center. They just had put it together, go to the virtual advising center, go to the virtual advising center. And all of us instructors had to sign up for at least 5 hours. I think I may have had either 6 or 7 hours. I don't remember now, but I had more than 5 to be advising. Okay. And we were in half-hour time slots, so that was at least 10 time slots a week, though I think I had more than that, maybe 12 or even 14, something like that, time slots a week. And I tell you, almost every week I had the vast majority of those time slots filled up. I can't remember a single time that I didn't have at least half of them filled up, and I think most of the time, many of the times I had absolutely everyone filled up, but usually had a few half-hour slots here and there missing. Okay, so anyway, I was advising students right and left all summer long, and we had a pretty good, it's not just me, but I think others were too, had a pretty good enrollment in the fall. This Banner system has some other issues. If you don't come to class the first week, it kicks you out. Or, as a few of you have done, submitted some type of work that first week, then you get to stay in the class too. Well, they kind of fiddled around and overcame that a little bit, and but then the way we do things, or they do things, or whatever, is after a while, if a student has not shown up in class, which should have been kicked out at the very beginning, we have another thing when they go back and kick students out. Okay, maybe those students trying to get back in the course, and then they still never show or attend, and then they get kicked out again. And then there's yet another time when, and this is a real problem with Banner, is that we can't tell when a student is paid or not paid. And maybe it doesn't matter that we shouldn't be able to tell that, except for the fact we don't know when a student has or hasn't paid, so we don't know when to be telling students, hey, please get paid, and stuff like that. So at some other place, they kick out all the students who haven't paid by that point in the term. And so we wound up with a little bit lower registration this fall than what we had anticipated. At one point, they said our registration was up to or very close to equal to what it was last fall, which was very good. And then the next round of purges came through, and we went back below that. But now Now, when we're expecting students to be registering for spring, I've been registered, down in the virtual advising center all term long for at least 5 hours. And so far, I have not had a single advisee to contact me through the virtual advising center. Not a one. Whereas last summer, much shorter summer and everything else, they were just every week we're there. Now they're not there at all. I have a feeling part of the culpability is the fact they weren't telling students to, now maybe they were, maybe I don't see student emails to go to virtual advising center and get advised so you can register for for spring. I haven't seen that because I haven't been. Now, could be also that because I'm retiring, they've moved all my advisees to other places, and maybe that's why I'm not seeing anybody. But I sort of doubt that's the case. Most of the time they aren't proactive like that. So I don't know. But anyway, what's the bottom line to this? Well, the bottom line is that very low registration for spring term. So here's how they're responding. Next week, Monday through Thursday of next week, they are having a huge push to get all students advised and registered for next spring. Okay? What they're going to be doing on both campuses, Bessemer campus and Birmingham campus. On the Birmingham campus, in that new Academic Success Center, that big new brick building right there on Wilson Road, where the Winona Elementary School used to sit, they are going to have some big room in that set up for students to come in and get advising. And you'll come in basically almost by your major and get advised for that. So they really are pushing for students to come in and do that. On the Bessemer campus, it's going to be in the Ethel Hall Auditorium. Now, it's not the same Ethel Hall building where the nursing program is on the East Campus of Birmingham. That's a different building. This is on the Bessemer campus, Ethel Hall Auditorium. There they'll have tables set up throughout that big room and spread out so that hopefully everybody will be able to maintain 6-foot separation. They're going to be advising between 9 in the morning and 7 in the evening, Monday through Thursday. There'll either be a faculty member, a staff member, or an administrator there at every table sometime every hour during that time frame. Now, I can't be there because of my health, and they don't want me there because of my health, but they're going to have people there. Sometimes it may be more than one person per table. It doesn't seem to make sense, but they may do that. The last list I saw indicated that some of the tables may have more than one, but there should be one person per table. And the students will maintain the 6 feet distancing. Everybody will have masks on. All that kind of stuff will be happening. Okay? Now, all that being said, here's what I would advise you to do. Get in touch with an advisor tomorrow. Sign up today, this evening, before you leave. See if you can get on some advisor schedule tomorrow. Now, if you can't, because this is right at the end of the week, and they may not, allow that this late, see if you can get on advising with a virtual advisor next week and get your advising done virtually, then register for your classes from a distance. I do not recommend going to campus. If you need to go to campus, okay? If you need the face-to-face advising with a plexiglass thing in between and stuff like that, go to campus. They have it set up for you to do, but if you can do it virtually and get registered virtually, do that. You won't be exposed as much. You'll be safer. But if you do need to go, go. Please go. They've got it all set up for next week for you to go. Okay. Any questions on that? Okay. Now the second announcement, and both of these, the second one was I put out as a Blackboard announcement. I don't know if any of you know Mr. Matthew West. He's a sociology instructor, also teaches history, and really good guy. He is working on his PhD at University of Alabama. And one of the courses he has to take is a statistics course. And in that statistics course, they have a project. And his project is to take a survey of students. And there's several things covered in the survey. One is just background information. Now, don't worry, your name, any information about you will not be made public or be visible to anyone. In fact, it may even be blind to Mr. West. I don't know about that part, but I know that it will be blind to anyone else. Okay? And it's going to be background information. Then, basically, your feelings on face-to-face classes, virtual classes like this one, or online classes. That will be part of the survey. And the other part is if you feel like COVID-19 has impacted or influenced the quality of your educational experience so far. Now, I don't know how those are phrased. I haven't read the survey. I'm not doing the survey. This is for students. But I put that out there under a Blackboard announcement. You'll probably have to copy that URL onto the command line to do the survey. But he claims it'll take only about 5 minutes to do the survey. Please, if you can, participate in that survey to help as much as you can. All right, those are two rather long announcements. Sorry about that. Do any of you have any issues, problems, concerns, whatever? All right, if not, here's a couple of other things I have done. I understand that Miss Winston, Valerie Winston, posted, oh, here comes Daniel. Let me get him in. Okay. And I'm stuck. Here we go. Daniel is here. All right. I believe Miss Winston, as she said she would do, got a form of the Lab 8 that we did last week done. I only had a couple of pieces of that done, but they weren't done before class. I think she, being a much better and faster typist than I am, was able to put something together. Well, since then, I had a little bit of time today that I was able to put together, before I knew she had done that, to put together a Lab 8 too. Some of you had already turned in Lab 8, just filling in the blanks without having blanks to put them in. You just wrote answers down. Any one of those things will be perfectly fine to submit for your Lab 8. That's the lab we did last week. Okay, and then in this 2 hours I had before this class, I was able to refine and correct a little bit the Lab 9 that we had from last summer. Okay, so that is also, let's see, was it last summer? No, last spring. So the Lab 9 is out there, and the link to the same place we always go, the Colorado PHET simulation. That link is out there as well. So that's what we'll be doing in lab today. It's the first lab for electricity chapter. All right, and we're just now today starting electricity. Any questions on anything we've done so far, how we're going to wind up the term, any of those kind of things? Okay, since I brought up winding up the term, we have this class today on chapter 6. Hopefully we'll get far enough along to have a lab today on chapter 6, the first lab on chapter 6. Then we'll have a class on chapter 6 Tuesday and hopefully Thursday of next week as well. Hopefully we will finish chapter 6 by Thursday of next week. If not, we still have some time we can go into the following. Then after that is Thanksgiving week. There are no classes during Thanksgiving week. After that, we come back and have 1 week, full week of class, and then this class, because it's a mini-term class, we have class that Tuesday of the following week after that one. Then at the end of Tuesday of that week, then I'll give you your final exam. It'll be a pretty easy exam, one that you can probably do in a fairly short period of time, and we'll do that. Here comes Brianna. Let me get her in and marked as present. Okay, Brianna's here. That gets us up 1, 2, 3, 4, 5, 6, 7. We should have 7 students here. Let's see what we got. Well, we only have 6. Okay, we must have lost somebody who came in earlier. Okay. Any questions from anybody about any of that stuff? So we have chapter 6, probably 3 labs, and chapter 8, and we may only have 1 lab for chapter 8. I only have 1 ready now, but if I can get a second one together, we'll probably have 2. We probably will not have 3 labs for chapter 8, and here's the reason. That last day we have class for chapter 8, that second Tuesday in December, that's the last day of class period. I don't want you having to work on the lab, work on chapter 8 test, and work on the final exam, all 3 due by Thursday. So more than likely on that Tuesday we will not have a lab that last Tuesday, and definitely not on the final exam day, which basically all it is you turn in the final exam whenever you can. A lot of times we have pizza, but we can't do that this year. Okay, sorry about that. All right, any questions? Okay, so we're getting ready to start chapter 6. Should have already been going at it for about 15 minutes now, but let's get going now. Chapter 6 is on electricity. I think the title should be Electricity and Magnetism. Okay, and why do I say that? Because both of these pieces are in here, and the chapter is split up that way. And this is an incredible picture here in the very front of the book. It's in your text. It's also on the slide set here. It looks a little fakey almost to me, because it looks like there's a really dense cloud covering here, and yet you see a full moon just perfectly well with no obstruction from clouds, which is a little bizarre. Most of the time, if you have that much lightning going on, you've got a pretty good cloud cover. So I find it sort of surprised that full moon is sitting there like that. But maybe it showed up that night that way. I kind of doubt it, but I guess it could. But anyway, why do they show lightning? Wouldn't that be in the weather chapter? Well, yeah, it probably is. But lightning is a form of electricity. So we will be talking about that a little bit later. Here's, if I could get the thing to advance. Here's the core concept, also on page 140 in your text, or 6-1 if you have the little book. Electric and magnetic fields interact and produce forces. That's why I said it's not just about electricity, it's electricity and magnetism. And we're going to be talking about the fields and that they interact and produce. Not just can produce, they do produce forces. Okay? So let's start with the concepts of electricity. This is 6.1. Now, we begin here talking about the electron theory of charge. Okay? For thousands of years, I'm sure, people had known about this Amber effect, they call it. Now, that's not Amber List or something like this. It's an Amber effect. And what was that? Well, they knew if they took a piece of amber, which I don't know if y'all are familiar what amber is, it's basically fossilized tree sap, okay? The color amber we get from fossilized tree sap, because tree sap is usually that sort of a light brownish, yellowish kind of color. And when it's fossilized, that tree sap is basically around that color. And people would find pieces of it, and they knew if they took a piece of it and rubbed it on fur or wool or something like that, and then snuck up behind a friend and put it against their neck or somewhere like that, they would get a shock. Okay? That was the ancient mystery called the Amber Effect. Now, that was a parlor game. It was things people did to one another, laugh and giggle and that kind of stuff, but no one knew really what was going on. Okay? A scientist named J.J. Thomson came along. Now, we had, goodness gracious, what was his name? Count Rumford. He was also a Thomson that we talked about at the last chapter. This is a different Thomson. J.J. Thomson, he, I'd say late 1800s, early 1900s, identified negatively charged electrons. That's what was happening with the amber effect. When you rub the amber with the fur, the electrons, which they didn't know what they were, but these charges came off the fur onto the amber, and then when you touch someone with it, they get a little shock. Nothing serious, just a little shock. It's called static electricity. Okay? Now, those were identified by J.J. Thomson. Okay? Pretty incredible how he came up with it and stuff. But anyway, that happened. Today, we understand a little bit better what's happening. We understand that the basic unit of matter today is the atom. Okay? And that's specifically the basic unit of an element. There are only a fixed number of elements. We know of probably about 100, something in the neighborhood of 120 elements. Okay? Some of those may not be around very long. They're very unstable, that kind of stuff. But something between 100 and 120 elements. Well, the smallest unit of each of those elements is an atom. Now, those elements and atoms combine in certain ways to form molecules and compounds. We talked about this in earlier chapters. Okay? Well, but still the basic unit is an atom. What are atoms made of? Well, this is something that's pretty incredible. I'm going to turn it around a little bit. An atom is made up of first a nucleus. Okay? Plural is nuclei, singular is nucleus. That nucleus contains protons, which are positively charged, and neutrons, which are neutrally charged, no charge at all. Okay, and that's in the nucleus. Neutrons, protons. Surrounding that is a cloud of electrons. Now, here is the mystifying and crazy way that's put together. That nucleus, those protons and neutrons, protons and neutrons, basically make up almost all the mass of that atom. And they are packed into a tiny, tiny, tiny little nucleus. Okay? And just about all the mass is in that nucleus. Now, surrounding that nucleus is a cloud of electrons. Okay, now those electrons have a little bit of mass, just a small amount, very, very little mass, about 1/10,000th of the mass of either a proton or a neutron. Okay, and yet they take up almost the entire volume of that atom, because the volume is occupied by that cloud of electrons. But in between those electrons, there's nothing there. There's nothing. It's empty space. So all the mass is concentrated, just about all the mass is concentrated on that tiny little nucleus. So even this illustration, that nucleus is probably way, way too big for that cloud of electrons that you have there. And yet all the mass is in here, and this is just taking up space. Those are those electrons flying around there taking up space. That's a three-dimensional ball, and the one they're showing here happens to be helium. I know that because helium has 2 protons, 2 neutrons, and therefore this cloud here would have 2 electrons. Now, how do I know that? Because the protons are positively charged, the electrons are negatively charged, the neutrons have no charge at all, they're neutral, and Basically, I don't even like this illustration here because basically there's not a ring of electrons out here. The electrons just, these two electrons in here are basically occupying just a little sphere, a pretty big sphere compared to that here. So that's your basic setup. So you have a positively charged nucleus, so many positive protons, so many neutral neutrons, and then a group of negatively charged electrons that fly around in a cloud, just dispersed in some cloud. Okay, now chapter 8 will go into this in more detail. Okay, but that's the setup. Now, why are we talking about it with electricity? Electricity is that charge component. Okay, so what is electric charge? This is charges that occur in matter. Protons are positively charged, electrons negatively charged. That's where charges come from in matter. This charge cannot be separated from the particles that have those charge. An electron cannot be separated from its charge. You cannot have a neutral electron. You cannot have a positive electron. Now, there is something in the nucleus called a positron, but we're not going there. Okay? You cannot have a neutral proton. It just doesn't happen. Okay? If you have a proton, it has a positive charge, period. If you have an electron, it has a negative charge, period. Okay? The charges are inseparable from those particles. The electrons have the negative charge, protons have the positive charge. Now, how do these charges interact with each other? Well, they interact with a force called an electric force. Okay? Remember when we talked about a gravitational force? The formula for an electric force is very, very similar for a gravitational force. Here is the basic rule. Like charges repel each other, unlike charges attract each other. Now remember with gravitation, any mass is attracted to any other mass. There is no repulsive force with gravity. It's all attractive. With charges, electric charges, you could either have a positive attractive force or a repulsive force. You can have both, and you do have both. Now here's another really bizarre feature. If you remember, I said that tiny little nucleus has just about all the mass of that atom in that tiny little nucleus, and yet the only charges in there are positive. Well, wait a minute. I thought positive charges, like charges, repelled each other. Why are nuclei not blowing up? Well, there's that other force. If you remember in, I think a couple chapters ago, we said there were these four basic forces. Gravitational force, which is very extended for large distances, but it was a weak force. Then you had electromagnetic forces that go for shorter distances but are stronger than gravitational. And then we had those other two, the weak nuclear force and the strong nuclear force. Now I hear dinging going on, but I see no new students in. We only have 6 students present now. 1, 2, 3, 4, 5, 6, 7 students have been here. One person must have left. Maybe that's what the dinging was. I don't know. So those nuclear forces, those within the nucleus, have to be incredibly strong because they're stronger than the electric force, which like charges would repel each other. So something's holding those protons together with the neutrons, and then the electrons, we know why they fly around on the outside, because they're being attracted by that positive nucleus. Okay, so that is electromagnetic force, or electrostatic force, I'll call it. Now, here's another term. An ion is a non-zero net charge that comes about from either the loss or gain of electrons. Okay, and we're going to illustrate that in just a minute, but remember back here, if you have 2 protons and 2 electrons, you're going to be neutral, and that's an atom. But if you've either picked up an extra proton or lost, I'm sorry, you don't ever pick up a proton, picked up an extra electron or lost an electron, then you wind up with either a positive charge if you lost an electron or a negative charge if you picked one up. Because these are the things that move around, the electrons. They're tiny, almost no mass. They can be exchanged, lost, gained, other things. The protons live in the nucleus. They don't go anywhere unless you have a nuclear reaction, and we hope you don't ever have one of those. Okay. So you get it from the loss or gain of electrons. That's what gives you, if it's a loss of electron, a positive charge, a gain of electrons, a negative charge, and those form ions, positive ions or negative ions. Okay. Now, this is a representation of, and I just happen to know this, a lithium atom. Okay, a neutral atom. And here's Jacob. Let me get him here, and we'll pick up with that thought in a moment. So Jacob's here. Now we're up to 1, 2, 3, 4, 5, 6, 7, 8 students present. Well, 8 students have been here anyway, but only 7 are present now. So we did lose somebody. Okay. Now, I happen to know that's a lithium atom. Why? Because it has 3 positive charges in the nucleus of that atom. Now, they don't show how many neutrons are there. They don't have any charge. Now, that nucleus would be incredibly smaller than those 3 positive charges indicate. Okay? But then outside of it is this cloud of only 3 electrons. 3 electrons because there's 3 protons, 3 electrons. That makes a neutral atom of lithium. Now, what they have done well here, the first 2 of those electrons tend to stay close to the nucleus in sort of a spherical cloud around there. You never know exactly where they are, but they're somewhere around that nucleus. That last little electron, that outer electron, is flying around out here. And that's why I said earlier, this is not a really good picture, because the 2 inner electrons are in the inner cloud. This would indicate there's an outer electron. You don't have an outer electron in helium. You just don't have it. If this were lithium and you had 1 more proton here and 1 more neutron here, then this would be a better rendition. But they showed this to be 2 and 2. That means 2 electrons. They would just be in the inner cloud, just like you see here. We'll talk about that later in the chemistry chapter, why that's true. Okay, that's chapter 8. Okay, now, lithium, because it has that one lonely little outer electron, it's really bad about losing that electron. Okay, because it's out there by itself, it's farther from the nucleus, it's not being held as tightly, it's very common for that to lose it. Okay, then it would have more protons than it had electrons. That would become a positive lithium ion. Okay, and that's what the next thing shows. That electron flies off somewhere, gets lost, usually doesn't get lost, but it goes off, and now you have a positive lithium ion. Now, you don't have to know it's lithium. Okay, now, 1 electron was removed, was yanked away by somebody else. Okay, now here's the thing that doesn't happen. They're just showing you this as a representation. They're also showing what if it picks up an electron. Lithium does not pick up extra electrons. It just wouldn't do it, because what would draw the extra electron in? It's balanced when it's 3 and 3. There's nothing to bring it in there. But if this were chlorine or something like that, it would just have so many plus charges it would be hard to tell. That would be very common for that to happen, but not with lithium. But don't worry about this. They're just illustrating this would be, if it ever happened, a negative ion. Why? It has more electrons than it has protons. plus 4 charge, minus 4 charge plus 3 charge, that would be a minus 1 charge. 1 electron has been added. It won't happen with lithium like they're showing here, but it would happen with other things. Okay? So they're just illustrating what we mean by ions. If you have lost an electron, you become a positive ion. If you gained an electron, you become a negative ion. Okay, that's all they're talking about there. Now, I've mentioned before, they're finally getting around to mention static electricity. Okay, now what do we mean by that? That's electrostatic charge. In other words, you've done something, added energy to a system, like rubbing the amber with wool or fur or something like that. And when you did that, that energy you added doing that moved electrons off of the fur onto the amber. But they just sit there. That's called a stationary charge, and that's where they get the term static electricity. Stationary, static. You form a stationary charge on that amber or whatever the object is you're doing. Now, what's the charging mechanism? What I just described was friction, but you could have other charging mechanisms. Okay, let's say you had that piece of amber which has a positive charge, and you go over and touch a piece of paper with it, and now some of that positive charge moves to the piece of paper. Now the paper becomes a positive charge. Okay? Or you could do this. Hold that amber close to a little bitty speck of paper, and now the amber with a negative charge is going to attract the positive charge from this piece of paper and move the electrons further away, because unlike like electrons repel, unlike electrons attract. But then this piece of paper with the electrons down here are going to be attracting the next piece of paper. That's called polarization. That's a reorientation of your charges induced without actually changing your net charge. If you touch the amber to the paper, you move those extra electrons, some of them, to the piece of paper. Now it actually becomes charged. If you hold it close to it and then it's attracted to it, that's polarization. The positive charges from the piece of paper move up near the negative charges on the amber, and then the negative charges on the piece of paper move as far as away as they can. So here's the illustration of that, or one. This is a gal combing her hair. And I'm going to tell you a couple of things that I know about her hair. Okay? And you'll say, how do you know this? Well, you'll get there. Number one, her hair is clean. Okay? Number two, her hair is dry. And number three, the air around her is very dry. How do I know that? Well, if her hair was oily, it doesn't move electrons as easily. Okay? If her hair was wet, it doesn't move electrons as easily. If the air was lots of moisture in it, it doesn't move electrons as easily. But as we have, her air starts off to be neutrally charged, some positive, some negative, same number, perfectly fine. She takes a rubber comb, which would be a lot like that piece of amber, and she would comb her hair with it. And as soon as she does, what happens? The electrons jump off of her hair onto the comb. Okay, now her various hair strands now becomes net positive charge because it lost electrons. And because they're net positive charge, rather than be nice and orderly like it was before she combed, now they start spreading away from each other because like charges repel each other. And since all those hair strands are positively charged, they try to get as far away from each other as they can. So rather than making her hair look better, she just made it look worse. Okay? Now, what she finds out about the comb, excuse me, is it becomes net negatively charged. It was neutral, same number of positive and negative charges. Now you have extra negative charges because she brushed the electrons off her hair onto the comb. Now you could take that comb, and if you had a little pile of paper, little bitty shreds of paper, and held the comb over that, that's when you would pick up and might actually make a chain of paper pieces, because you've induced a charge, polarized those uh, pieces of paper. And this picture, I think, shows that. Now, these are big pieces of paper. You'd have to have little bitty torn pieces of paper. Okay, get that net negative charge on the comb, hold near the piece of paper. Don't touch it. Don't touch it. Hold it near the piece of paper. It's going to draw the positive charges from the paper toward the comb, pushing the electrons, the negative charges, away from the comb. Well, you do that to this one. Here's how the paper, it's not regular pieces like this, but little bitty shreds of paper. It starts off being neutrally spaced. It's still neutral, but it's reoriented. That's polarization. You've now pulled the positive charges up this way, pushed the electrons down this way. The next piece of, goodness gracious, the next piece of paper down would then do the same thing, and now you polarized, reoriented an induced charge without changing the net charge. Now, unfortunately, I don't know if I could show one in this room, maybe not. We live in an old house built in 1930s, and there's plenty of dust particles in this old house. Okay, dust particles, because they're so incredibly tiny, they tend to have a net positive or negative charge. Okay, and if these little tiny little dust particles, they're called colloids, by the way, so small they're net charges. If one positive then attracts a negative, attracts a positive, attracts a negative, attracts a positive, you get what you call cobwebs. If you've ever reached up and touched a cobweb. Now, if it's a spider web, you can feel it sticky. That's really a web. But if it's a cobweb, you reach up and touch it and it all falls apart. That's because it wasn't a web at all. It was charges, either actually charged or polarized, so they hung one after another and formed cobwebs. Okay? So touch one sometime if you can find one. If it falls apart, that was a cobweb as opposed to being sticky, which was a spider web. Oh, and here comes Thomas. Let me see if I can get him in and mark him present. Okay, Thomas is here. Okay, we're finally building up a fairly good sized class. That's 5, 6, 7, 8, 9. We've got enough for or at least we've had enough for a baseball team, but we only have 8 here now, so we did lose somebody. All right. Any questions so far? Thomas, we're in chapter 6, electricity, though I would call it electricity and magnetism, and we're around about page 143, which would be 6-4 in your text. Okay? Talking about static electricity. Let's see if we can advance past the slide. There we go. Now, there is a little blurb there on, well, there was one on Science Sketch, which says draw a picture. So you can do that if you're interested. I'll let you decide that. There was a concept supplied on page 143, static charge, and that's a pretty interesting little thing. I think you can probably do that on your own as well. And then we hit electrical and conductors and insulators. This is the very bottom of page 143 or 6-4, and then moving on from there. So let's hit it here. Now, what do we mean by electrical conductor? Electrical conductor has electrons that are free to move throughout the material. Now, if you add charges to a conductor, they dissipate as fast as they can. Okay? Now, two general types of materials that are good conductors. One are metals. Now, we'll talk about metals in the next chapter as well, chapter 8. But the metals are materials that have what they call free electrons. Now, if you think you may have heard that somewhere before, think back to the last chapter when we talked about being good heat conductors, and sure enough, those are the free electrons. Okay, now graphite, which is a form of carbon, also is a pretty good conductor. Now, that's not because it has free electrons, but it passes electrons on it. Carbon can either be +4 or -4. Okay, well, neither one of those is very likely to happen, so it exchanges electrons pretty easily. Okay, they're not free electrons, but it does a change. Metals, however, has just this cloud of electrons that easily go back and forth between the atoms. They don't actually belong to any one particular atom. Now, on the other hand, what's a electrical insulator? In the last chapter, chapter 4, we talked about thermal insulators. Now we're talking about electrical insulators. And basically, what you wind up with, same type of materials. If it was a good thermal insulator, it's going to be a good electrical insulator. If it was a good electrical conductor, it was a good thermal conductor as well. In these, the electron motions are restricted. The electrons are not free to move from one atom to another, to another, to another. They are restricted. The added charge tends to remain on an object. Amber was a good electrical insulator because the charge, when you rubbed it with wool or rubbed it with fur, the charge stayed on that until you were able to discharge it. So in general, glass, wood, and believe it or not, diamond. Graphite is two-dimensional diamond. Tobias. Ha! He's the one that must have been here before and now come back. So now we should be back up to our 9 students. Okay, let's see if we're back up to 9. Yes, we're back up to 9 students. Welcome back, Tobias. Glad you could get back in. Okay. Graphite, good conductor, because its electron configuration is in two-dimensional sheets and the electrons are pretty free to move, whereas diamond is in a three-dimensional crystal lattice and those electrons are nailed in place. They do not move. So even though that's the same material, carbon, same atoms, carbon, because this is a two-dimensional crystal structure, it makes for a great insulator, whereas diamond is a three-dimensional crystal structure, terrible insulator. Well, certainly graphite, which is basically almost the soot that you find on your anytime you burn anything, ugly black, you know, that kind of stuff, and diamond, which is that beautiful sparkling girl's best friend, completely different seeming materials because their crystal structure is so different. Now, you have in between conductors and insulators things called semiconductors. They will conduct or insulate depending on the circumstances. It could be a temperature issue, it could be a directional issue, it could be a lot of things. Now, applications of those, your computer chips. If you've heard people talk about Silicon Valley in California, that was because silicon is one of those semiconductors, and that's what they made a lot of the earlier computer chips with. They may probably still make quite a few with those, but they have other materials as well. Solar cells are made out of semiconductors. The energy comes in from the sun and dissipates one way but doesn't go the other way. Those are semiconductors. The whole basis of transistors and other modern electrical setups. Okay, semiconductors. In the next chapter, we'll talk a bit more about them. So these two next chapters, 6 and 8, really tie together very well. Now let's go back to that concept of electric charge. We said a single electron has a negative charge, a single proton has a positive charge. You never run into single protons, hardly ever. I mean, it just wouldn't happen. Electrons, though, yep, they're all over the place. Protons are stuck inside that nucleus, okay? So, electrons and protons are submicroscopic materials. I mean, just tiny, incredibly tiny. Nothing you can measure, okay? However, our unit for charge is a coulomb. Capital C here, named after Charles Coulomb, an early French physicist who did a lot of work with charge. They named the unit. His name was Coulomb. They spelled the Coulomb with a little c, but put the abbreviation with the capital C. Now, remember back in thermometry, we talked about degrees Celsius. And that's one reason they have to have the degree symbol by it. If you didn't, you wouldn't be able to tell if they're talking about coulombs or Celsius. So a degree symbol is required for a Celsius. No degree symbol means you're talking, capital C means you're talking about coulombs. Now, when I said macroscopic and microscopic, it takes 1 coulomb of charge, one single coulomb of charge, is equivalent to the charge of 6.24 times 10 to the 18 electrons. Now, what are we talking about there? 6.240 comma 0, I'm sorry, 6 comma 240 comma 000 comma 00 comma 3 zeros comma 000 comma 000 comma. You'd have 5 groups of those 3 sets of electrons, I mean zeros, okay? The first would be thousands, the next would be millions, the next would be billions, the next would be trillions, the next would be quadrillions. I don't know. I don't even know what number it would be up to when you got up to 18 of them. 18 sets of those, with that last 18th set being a 240 rather than 000, and then a comma with a 6 in front of it. That's how many electrons makes 1 coulomb of charge. 1 coulomb of charge is a macroscopic quantity we can measure with equipment and stuff. A electron, you'll never measure the charge on an electron. Now, some people have, but they did it not directly, they did it indirectly. This is the metric, or the SI unit of charge, is the coulomb. Now, the English or U.S. customary system does not have a separate measurement. Electricity came along after the French Revolution, so once they started identifying terms, everybody uses the same one. The British didn't use something different from the French. Okay. Now, what is an electron charge? That is the smallest, the absolutely smallest charge you can ever have in nature. You cannot get less charge than 1 electron charge. That's a fundamental charge, smallest seen in nature. Now, the quantity of charge is related to the quantity of electrons. Just like we said here, 6.24 times 10 to the 18 electrons makes 1 unit of Coulomb charge. Now, going the other way, since 1 coulomb of charge, now remember in the last chapter I said capital Q represented a quantity of heat, measured usually in calories. In this chapter, little q represents the quantity of charge, represented by coulombs. And 1 coulomb of charge is equal to some number, there it is, 6.23 times 10 to the 18th, times that many electrons, single electron charges. That's the number of electrons times the individual electron charge. So if you had just a small fraction of that, you would have a fraction of a coulomb, like a millicoulomb or a microcoulomb. Okay, but to have this number of charges, 6.24 times 10 to the 18 electrons, that's a lot of electrons. That gives you 1 coulomb of charge. Now you can also divide both sides of this equation by that same n, 6.24 times 10 to the 18th electrons, and you're going to get a number then that would be an individual charge on an electron that would be 1 coulomb, that's the Q on top, divided by your 6.24 times 10 to the 18 electrons on bottom. That would give you 1.60, pull out your calculator and do it, times 10 to the minus 19 coulombs per electron. So you talk about a small number, that's 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 to be a single electron charge. Incredibly small unit. Okay? Whereas this is an incredibly tremendous number of electrons to make 1 coulomb of charge. Now, make sure I'm not skipping anything here. Before we get to electric forces, let's go back a slide, and maybe here. If I can find my pen, there it is. Example 6.1. Combing your hair on a day of low humidity. Remember I said that gal had to be a dry day and her hair had to be clean and dry. So low humidity results in a comb with a negative charge on the order of, okay, got to get my pad here too, negative charge on the order of, where are you, pen? There we are. Okay, here we go. A charge is, in this chapter, little q on the order of 1.00 times 10 to the minus 18 coulombs. Minus 8 coulombs, I misread. Minus 8 coulombs. That's the charge measured in coulombs. How many electrons were transferred from your hair to the comb on that day? Well, probably not my hair. I don't have enough of it to transfer that many, but that's beside the point. Okay? We know from the formula we just had that the number of electrons, that Q, is equal to that fixed number, this one right here, that's your N right there, times your electron charge. And since we are looking for the number of electrons, we divide by the electron charge. So divide both sides by your electron charge, which for some reason this isn't doing. Okay, and these go out, and you have N equal your charge, 1.0, I'm sorry, we're looking for, wait a minute, let me get, Tobias must have got kicked out again, now back in, glad you're back in. Okay, how many electrons were transferred from your hair? So this N is not that. This is what we're looking for here. It's 1.00 times 10 to the minus 8 coulombs divided by, and then that unit that we had a little earlier, I'm going to pop it up here again, this one right here, 1.60 times 10 to the minus 19 coulombs divided by the electron charge is 1.60 times 10 to the minus 19 electrons. Now I'm going to put them the symbol like that. Okay, Now, pull out your handy dandy calculators. Now, I don't know how y'all are with scientific notation. I think we've done enough that hopefully you're able to do this. Okay, I've got to get my phone turned on and my utilities and calculator up here. Scientific notation, I'm going to have to be in scientific calculator mode like that, held sideways. So it's 1. You don't need to type in the 0.00. Your calculator will deal with that. Now, instead of typing in times 10, you press the EE key. Now, some of your calculators may be EXP key, but on mine it happens to be that EE. Oh, where is it, right? There it is, EE. If you have an EXP key, that works as well. Okay, 1 EE, and then to the -8. Now, if you have a real scientific calculator, you probably can hit that little negative sign that's in parentheses. That's your negation kind. I don't have one on here. I have a sign up here that changes sign. So I have to enter the 8 first, and then that key that says plus minus, that changes the +8 to a -8. Okay, then I'm going to divide that number by, and by the way, that's that number without the scientific notation. You see there's 7 zeros and a 1 after that decimal. Pretty small number. Divide that by 1.6, and you don't need the extra 0 there, but you could put it if you wanted to. EE -19. So I have to press the 19 first, then change signs, then hit equal. Look how many electrons we're talking about. 62.5 billion electrons. Okay, I'm not going to write all those zeros down there. I'm going to write this in scientific notation, and that would be, I don't know why this thing is doing stupid stuff like this, but it's doing it. Okay, this N would be on the order of 6.25 times 10 to the, and count how many zeros you have there, or how many decimal places you have. 3, 6, 9, and one more would be 10. So 6.25 times 10 to the 10th electrons. That's what we're talking about, because this unit down here was electrons per coulomb. The per coulomb here, no, I'm sorry, this was coulombs per electron. Sorry, let me go back and get that corrected. Where is my, there it is. Okay, this was how many. Okay, I hear something else ringing. Don't know what that means. This is how many coulombs per electron. Where in the world is my pen? I cannot find it on here. Oh, there it is. Okay, this is coulombs per electron. Okay, let's see if anyone is in the waiting room. Nope, we've still got our 9 students, which is good. I wish we had more. Okay, so what did they get in the book? 6.25 times 10 to the 10th electrons. Now I put a little minus sign with my electron. They don't in the book. That reminds me, I'm talking about E, not the number E, which is the natural base of our number system. That's 2.71 blah 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 blah. Nor are we talking about an exponential. That's related to that. We're talking about electrons. So I put the minus sign, reminding me I'm talking about electrons. Okay, you may not need to be reminded of that, but I found it helpful. Okay, so that was example 0.61. All right, so now let's move on to that's the numbers we used, electrostatic forces. Now, not only was Coulomb the guy they named the unit for, like I said, he did so much of the earlier work in charges, they actually named this law after him as well. The law that relates electrostatic forces to, nature. This is Coulomb's law. It's a relationship giving the force between two charges. Now remember, gravitational force, that was the law. It was called Newton's law of universal gravitation. That gave the relationship between giving the force between two masses. Now we're doing with Coulomb's law the relationship giving the force between two charges. Similar in the way it's put together as Newton's gravitational law, but you'll see the constants are incredibly different. Okay, so here's the one for Coulomb's law. The force between any two charges is is proportional to the product of the masses, product of the charges divided by the distance between them squared. Look, the goodness gracious, I just said it. Constant proportionality, I can't get it out there. That's your K. That's what we're going to be comparing. So it's the product of the charge of the first times the charge of the second divided by the distance between them squared. Okay? Now, this Coulomb force constant, also called the electrostatic force constant, is 9.00 times 10 to the 9th Newton meter squared per Coulomb squared. Okay? Now, if you remember back when we did Newton's law of gravitation, now remember, the forces are measured in newtons. That's why you have newtons in both of those. The distances are measured in meters. So when you have a distance squared here, you got a meter squared here. But with Newton's gravitational law, you're dealing with kilograms of mass here. A kilogram of mass is a big amount of mass, and you got two of them multiplied together. A coulomb of charge, though, is a very small amount of charge. So it's not too surprising that this is going to have a lot bigger number. But when you look at how much bigger the number is, the Newton's capital G, universal gravitational constant, I don't remember the exact number, 1.60 or something like that. I don't think that's it. Times 10 to the minus 11. That is an incredibly small number. This one is positive 9. That is a difference of 20 orders of magnitude. One with 20 zeros after it. That would be 10, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. That's the ratio between this constant, electrostatic constant, and Newton's constant of gravitation. So that implies that the K, since it's so much bigger than the G, that gravity is a weaker force. It goes for a lot longer distance, but it's a much weaker force. Okay. Here was at 6.67 times 10 to the minus 11 Newton. Now this is not correct here. This is Newton meter squared, not meter. Newton meter squared per kilogram squared. Okay, now they put the G up here, they put the K down here. It doesn't matter, that's the same place. But this is 10 to the minus 11, the other was 10 to the positive 9. That's an enormous difference. And here they're going to show the ratio between those is 9.00 times 10 to the 9th divided by 6.67 times 10 to the minus 11. You probably can't see it now because they put that stupid block in the way. and that comes up being 1.4. You probably should have another digit there, times 10 to the positive 20. So that electrostatic constant is way, 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 way bigger than the gravitational constant. I mean, incredibly larger. Okay. Now, that was electrostatic forces. Before we get into electrostatic fields, or force fields as they call it, let's do example 6.2. Okay, so here we go. I'm going to clear the screen just temporarily here because I've still got that little 2 up there. Okay, so let's get rid of it. Electrons carry a negative charge, electric charge, and revolve around the nucleus of an atom. We've already said that. Which carries a positive electric charge from the proton. The electron is held in orbit, I'm sorry, I'm going to have to get some caffeine. I'm sorry, this anemia is just so far into the afternoon, especially on a Thursday afternoon. I just don't have any energy left. Hold on, sorry about this. Sorry, but I'm about to lose it. Okay. So, electrons carry a negative electric charge and revolve around the nucleus of an atom, which carries a positive electric charge from the proton. The electron is held in orbit by the force of the electrical attraction between the proton and the electron. Now, that sounds a lot like the sun. The sun has a huge, huge, huge mass. The earth has a pretty good sized mass. The reason the earth goes around the sun is that attraction between their masses. The reason the electron is held in orbit around the proton is because of the charges. Now, the difference is the distances. The distance between the sun and the earth is about 93 million miles. That's an incredibly large distance, but of course those masses are incredibly large masses. The distance between the proton and the electron, whoa, here it is. That d for the proton and electron, that distance between them is 1.00, this is typical, 1.00 times 10 to the minus 10 meters, which is an incredibly small number, 10 to the minus 10 meters. Okay? It says, what is the force of the electrical attraction between the proton and the electron? Well, that comes from Coulomb's law. F is equal to that K, which is your electrostatic constant we've talked about before, times Q1, which is the charge on the electron, Q2, which is the charge on the proton. Guess what? They're the same charge. Just because a proton's bigger, it doesn't have any different size of charge, divided by this d squared. There's your formula. So what we're looking for here is what are the force. So we're looking for this. So this would be 9.00, and why it put that line there I don't know, times 10 to the 9th okay, times, now you might say, what are these charges? Well, we were given those earlier. Remember, the charge due to an electron or a proton, remember it's the same charge, they're opposite signs but they are the same charge, and that was the 1.60 If I could get my pen to show up again. Where are you, pen? There we are. I think somewhere in here. That pen just disappears like here we go. 1.60 times 10 to the minus 19 coulombs times 1.60 times 10 to the minus 19 coulombs divided by your distance squared, 1.00 times 10 to the minus 10 meters squared. Okay, now I forgot to put my units down here. The units here were Newton meter squared per coulomb squared. Okay, now I'm going to move my book out of my lap. I'm just too tired to even hold the book, and I need Coke is way too sweet. Need to cut that with a little bit of water there. All right, now I'm going to pull out my calculator and see what we get here. Okay, now get my calculator in calculator mode, and because I'm going to be doing scientific notation, I'm going to turn it sideways and get it in that. So we'll first type in the 9. You don't have to do the 0.00. Instead of doing times 10, you hit the EE or EXP key, and then you press 9. That's 9 EE 9, and you just see a 9 there, times, and then it's a 1.6. You could put the 0 if you want to, but you don't need to. EE, and for mine I have to do the 19 first, and then do the change sign and make it a minus 19, times 1.6 EE 19, make it minus, divided by, okay, now here I'm going to open parentheses. The reason is, same reason I've got the parentheses here. It's this number down here you're squaring before you divide. So you have to do that. Okay? So that's going to be 1 EE 10, change sign and make it minus, close that parentheses and square that number. Okay? And then press equal. Alright. Now I get a very small number. Count how many zeros are after that 0. 1, 2, 3, 4, 5, 6. I'm having trouble holding it still. 1, 2, 3, yuck! I just lost it. I hit some button and it blew it for me. Sorry about that. I've got to go back and redo all that again. Hopefully some of you have it. That's 9 EE 9 times, yep, that's right, 1.6 EE negative 19, so I press the 19, then the negation key. Okay, times 1.6 EE, do another 19 and another negation key, and then divide by, and here's where you have to open your parentheses. Open the parentheses, and that's 1 EE 10, change sign, make it negative, close the parentheses, square it, and then press equal. Okay, that's what I had before, but I'm having trouble counting because I have fat fingers on a very little thing. Let's count how many zeros. 1, 2, 3, 4, 5, 6, 7, and then between the 2 and the 3 would be 8. So this gives me something, if I punched in my numbers right, which sometimes I don't, this would be something on the order of, where in the world is my pen now? Oh, there it is. Okay, approximately 2.3, and they'll probably have 2.30 times 10 to the minus, how would I say, 1, 2, 3, 4, 5, 6, 7, 8, 10 to the minus 8. And what units? Okay, well, here we see a coulomb up here times another coulomb up here cancels out the coulomb squared down here. This meter squared up here cancels out the meter squared here, and this gives you newtons, which is a great unit for force. So this is your electrostatic force being that. And now that seems like an incredibly small number, doesn't it? Okay, but when you think about the distance you're talking about, that's an incredibly large number. I mean, that is really, really monstrous of a number, just because you're talking about such tiny, tiny little quantities. That's a lot of newtons. Okay, let's see what they got in the book. Page 145, right hand column, 2.30 times 10 to the minus 8 newtons. Okay, that's a pretty strong force, way bigger than the force of gravity, because the the masses of electrons and protons would be so incredibly small here. Gravity would be negligible. It would be so much less than that number. So electrostatic force wins. Okay, now I'm going to bury that for now, and let's move to force fields. All right, how do these forces act through space? If you think about, I already mentioned the sun's way over there, 93 million miles away is the Earth. Okay, how is the sun able to pull on the Earth? Well, gravitational forces act through force fields. Okay, electrostatic forces also act through force fields. The difference being, electrostatic forces can either be repulsive or attractive, whereas gravitational fields are always attractive. So charges are surrounded by these imaginary lines, you might say, that we call force fields, electric fields. These are vector fields. They have directions. They're either pointing toward the charges or pointing away from the charges. Now in gravitational, they're always pointing toward, okay? But in electrostatic fields, we have some pointing away, some pointing toward. Now, the fields and the charges are inseparable, okay? You can't have one without the other. If you have a charge, any charge out here, there's fields all around that charge. A charge over here, fields all around that charge, okay? They are completely inseparable. The fields act on other charges. Now, the directions of the fields would be the motion that a small positive test charge would have if you put it in the field. So let's imagine we have a positive field here. That's a proton or a positive charge here. Okay, it could be a piece of glass or something like that that is a positive charge. Okay, now if you put a little bitty test charge there, positive test charge, it would be pushed away, wouldn't it? Because like charges repel each other. So therefore, positive charges always have the field lines going away from them. Always have it going away. And they go away in 3 dimensions, okay? Evenly spaced generally. So a negative charge, if this was a negative charge, like a comb that you've combed your hair with or something like that, the force field lines are always pointing toward that, because if you were to put a little positive charge there, it would be attracted to that negative charge. So the idea is that the force field lines for positive charges are always pointing away from the charge, for negative charges are pointing toward the charge. Keep that in mind. Visualize that as your lines of force. Okay? Now, the same ideas applies to gravity and magnetism. Gravity, though, is always pointing toward. Magnetism, very similar to electrical. You have north poles and south poles. North poles, they're pointing away. South poles are pointing toward. Gravity, always pointing toward. Okay? But the same idea of force at a distance, the force fields. It's those field lines that control everything. Now, here's what I was just saying. The field lines always point toward a negative charge, because if you put a little positive test charge, it's going to be yanked toward that. And always point away from a positive charge, because a little positive test charge is always going to be pushed away. So the field lines point toward negative charges and always point away from positive charges. That's the rule for your field lines. Okay? Now, this is not advancing well. Let me see if I can go backwards. I can't. Okay? I'm hoping you've got your book open. Okay? And sometimes the slide shows up and sometimes it doesn't. But here's the upper part of that slide. Okay? The one I just tried to show. These are a positive and a negative charge. The positive on the left, the negative on the right. Okay? The field lines always point away from the positive charge toward the negative charges. So therefore, you put them close to each other, they're yanking each other so closely together, they're going to collide if you don't hold them apart. Okay? That's exactly why unlike charges attract each other. On the other hand, how many hands do you have? Okay. If you had these happen to be positive charges here, and put them close to each other, the field lines are pointing away from the positive charge, but these are pointing away from the positive charge. So there's no attraction. It's like a spring. They're pushing each other apart. Pushing each other apart, because these lines are going this way, these lines are going this way. The closer you try to get them, the stronger they're pushing apart. So that's what happens with two positive charges. Same thing with two negative charges, only then all the field lines are pointing toward the negative charges, and again, they're pushing each other apart. But if one of these was positive and one were negative, these arrows would be pointing this way, these pointing that way. Ying! They're pulling each other together like crazy. Okay? So there's what we mean by your force field or your field lines. There's the one for positive and negative. Okay, I didn't go enough things, but usually after I look and look and look for them, then they'll pop up there. So here's the positive of the field lines going away from the positive charges. Here's the negative charge of the field lines going toward. See how they link up like crazy, pulling each other closer and closer and closer together. That's why unlike charges attract each other. Okay. Now, the next subtopic here is electric potential. Okay? Now, electric potential, whereas electric fields and forces are both vector quantities that have directions with them, electric potential is a scalar field. There is no direction associated with it. It's a scalar field associated with potential energy. Well, that kind of makes sense, because a force is a vector quantity, energy is a scalar quantity. Okay? Now, the unit for this electric potential is the unit called a volt. Okay? Now, we don't have this unit exactly in the rest of physics. Most of the things we talk about, the units, like a force is a Newton, whether it's electrical force, a magnetic force, a gravitational force, whatever kind of force, that's going to be a Newton. Okay? Energy is usually a joule. Okay? Well, this isn't energy, it's associated with potential energy. Okay? And here's how this comes about. It's related to the work, which is energy, involved with positioning charges. So if you had a charge here already in place, positive or negative, whichever, and then you have another one here, and you're trying to hold it in place. If those charges are like charges, it's trying to fly this way, and you're holding it in place this way. If these were unlike charges, then it's going to try to be pulled this way, so you're having to hold it away. Okay? So it's not just the force in newtons, it is the potential, the work in joules is potential that is doing based on the number of charges that is. So basically what a volt is the work per unit charge. The potential difference important in producing forces and moving charges. It's analogous to masses in gravitational fields, okay, so to speak. Okay, so that's I don't like them saying electric potential is analogous to a mass. That just doesn't quite ring true, but in some senses it is. Okay, so let's see the units. Okay, if this is a coulomb of charge here, a positive coulomb of charge, and you brought in another positive coulomb of charge, and you're trying to bring it closer, you're having to do work, a lot of work, to get that to get close to that charge. Now, if it was within 1 meter of that charge, which is not all that close, you've done a joule of work. And remember, a joule, though, is a very small amount of work. So it's a joule per coulomb. Okay? That's what you're dealing with. That's what voltage is. That's what your potential difference is, joules per coulomb. Okay? And here is the formula for it. Electric potential difference. The symbol here is capital V for voltage. Now this is one place in physics where your parameter is the same as your units. If you think about what work is, the parameter is capital W, standing for work. The unit is joule. Okay? This is voltage, capital V. Your units is volts, which is also capital V. So don't let that confuse you. This V stands for electric potential energy. That V stands for how many volts. This is always preceded by a number. This is a standalone literal equation. This work, capital W, that's the unit. That's the parameter. The unit for that was joules. A capital W with a number in front of it would be a watt, which has nothing, well, not too much to do with this. Q here is not the Q we used in the last chapter for heat. This Q is your Q for charge. So voltage is energy per unit charge, work per unit charge, joules per coulomb. A volt is a joule per coulomb. Voltage, potential difference, is work per unit charge. So keep those straight. The V, capital V, stands for both of them. And the reason it's a capital V, named after an Italian scientist named Alessandro Volta. Okay? A really brilliant guy, lived in Lake Como, Italy. And the reason I remember that is my wife had professional meetings in Lake Como, Italy. Just happened to be the week between a spring and summer, or summer and fall term, and I got to go with her. Okay? And also her niece got to go with us as well. So when Karen was busy in meetings, Julie and I got to travel around the city, take a boat ride, and we ran across this beautiful little monument there. We went to see what it was about. It was where Alessandro Volta did much of his work on electric potential. Okay, they named the unit after him. Okay, Alessandro Volta. All right, so let's move from electric potential to electric current. This is 6.2 on page 147 or 6.8. Okay, now earlier we were talking about electrostatics, Coulomb's law, the electric potential between two charges. In that context, the charges are more or less fixed in place. They're not moving around, they're fixed. You comb your hair with a rubber comb, your electrons go off of your hair onto the comb, then you pick up pieces of paper, they're pretty much fixed in place. With electric current, current means moving charge. Now the charges are allowed to move. That means you're dealing with conductors, that the charges are free to move in those conductors, are pretty close to being free to move. What electric current is the flow of charge. What is charge measured in? Coulombs. And flow means charge is moving, so that would be coulombs per second. Just like distance per unit time is displacement, that would be like a velocity or a speed. Well, flow of charge would be coulombs per unit time. Why would the charge flow? Because you have that potential difference between the 2 points. So one is a positive potential, this is a negative potential, the charges are moving one way or another. So electric circuits are structures designed to localize, and I don't like the term utilize, use currents. Okay, that's what a circuit does. It either localizes those currents, fixes them in place somewhere, and uses the energy from those currents. Now if you think back on it, what was voltage? Energy per unit charge. So if you have a voltage between and a charge between that, it's the energy between those charges are your volts. Okay, now let's move to the electric circuit. This is on page 148. Now the structure of an electric circuit, you just about always have to have a voltage supply, a potential difference. That's your energy input. That gives the energy to the individual charges. Voltage is energy per unit charge. It's necessary to keep the flow of electrons moving. If you don't have a voltage, you're not going to have electric circuit, electric current. Now the circuit elements are in there. They use that energy that the battery or the voltage source supplied for you. Okay, they may be producing heat like a little space heater. They may be producing light like a light bulb. They may be doing some other type of work like moving soil around or whatever. That is the circuit element. Okay, the electric lawnmower would be cutting your grass, whatever it would be. Now the current flow convention, this is a little confusing here because the rest of physics, everywhere in physics, you always talk about movement going from high potential to low potential. Remember, high temperature to low temperature, high energy to low energy. It always moves in that direction. But because electricity has two different charges, okay, and it just was sort of arbitrary that someone decided to name the electron a negative charge and the proton a positive charge, that makes everything sort of backwards because it's the electrons that are moving, not the protons. Well, since they're a negative charge, they move in the opposite direction from what you would expect. So the current flow convention, the convention is it goes from high potential to low potential through the external circuit. Now, that's tradition. That's what we usually name it as. When we talk about electron flow, and most of the time it is electrons that are moving, they go in the opposite direction. So the conventional current goes from high potential to low potential. The electron current actually goes from low potential to high potential because the electrons are negatively charged. Okay, just because I think they blamed that on good old Benjamin Franklin. He arbitrarily, I think, was the one who named electrons negative. I don't know. J.J. Thomson may have done it. Who knows? Now, here's the water pump analogy. Okay? Now, your voltage source is the source of your energy. Okay? Maintains that potential difference. Now, the way they've drawn it here, this is the positive pole, there's the negative pole. And our conventional current goes from positive to negative. So the voltage source adds the energy to the charge, energy per unit charge. This bumps it up. Now, if that were really a car battery, that's usually about a 12-volt battery, giving 12 volts to every coulomb of charge, 12 joules to every coulomb of charge. That's what 12 volts does. Comes over here to the light bulb, and now the voltage has a drop here. It's a higher potential on this side, lower potential on that side, because we assume the conducting wire basically has very little to no voltage drop, because that's just conducting the electricity. So this pole here would be the same as your positive pole on the battery. This would be the same as the negative pole on the battery. So you have a 12-volt drop here. Okay? That means work is being done here. That light bulb shines, and if you were to feel of it, it would also be quite hot. Remember the last couple of labs that we've had, that incandescent bulb will produce an awful lot of heat. Compact fluorescents produce a little heat, and even LEDs will produce a little heat. But mostly they're trying to produce light. So that's where the energy is going to produce light here and some heat. That energy that the battery gave to those electrons, now the electrons are losing energy. You don't lose electrons, you lose the energy of the electrons. And they are giving off the energy here, producing the light and possibly heat. And then the electrons make their way back to the battery and get charged again. They are boosted in energy here and lose energy here, producing light, sound, whatever. Okay. Now, the water pump analogy, you have a pump over here that's pumping the water up here, giving it higher potential energy here than it had down here. Okay, the water then comes through here, falls and hits the water wheel, turns the water wheel, and maybe lights up a light bulb or makes electrical generation or does something, and then the water returns to the pump and goes back up again. Well, how are those two related? The pump here is a lot like the battery. It gives more energy to the charge. So the water is like the individual charge. Okay? The pump gives more energy to the water, and then that energy is transmitted from the drop here to kinetic energy to turn the water wheel, which could make an electric current, it could make a light bulb come on, it could do all sorts of things there. And then the water or the charge returns to the battery to get pumped up again. Okay, so there's your electric water pump analogy to electric circuit. Now, all analogies will sort of fall apart if you take them too far. If you were to puncture this line here, then the water spills out. If you were to break the wire here, the electrons don't go spilling out, it just stops. Everything stops because you don't have any potential difference. You don't have a conducting wire to keep everything connected. Here, water would spill. Here, the current stops. That's called a short a broken circuit, open circuit. Okay, we'll talk about that a little bit later. Okay, now let's move on to, now they did skip one thing here they should have put in. And let's see, maybe they're going to put it in here. Not yet. Let me put it in here. Here. Okay. It's a pretty important concept. Okay. They give it on the top of page 149, but they don't show it in the PowerPoint. Okay. And here's what we've got. We're talking about electric current. Now the symbol for electric current, and I don't know why, I have no idea why, is I. Sometimes it's a capital I, sometimes it's a little I. We're going to use capital I because that's what the book does. What current is, and I mentioned it before, it's charge per unit time. Remember back here, the flow of charge, at that point I said this is charge per unit time, just like displacement per unit time is velocity, charge per unit time is current. Okay? Now this is the parametric equation. I stands for current, Q stands for charge, T stands for time. What are the units for this? The units for this is an ampere, named after another brilliant French physicist who studied charge, and his name was goodness, I can't remember his first name now, but his last name was Ampere, and so they named the unit of charge ampere after him, so they make it a capital letter. Quite often we'll abbreviate that and say amps. You'll hear amps more than ampere, but it's the same thing. Q, of course, is coulombs, and time is measured in second. So 1 amp is equal to 1 coulomb per second. The flow of charge. 1 amp is 1 coulomb per second. Now, if you remember, a coulomb is a reasonable amount of charge. In fact, it's a pretty large amount of charge. An amp is a pretty large amount of current. So quite often when we're dealing with currents, we'll be dealing with milliamps, okay? And sometimes with charges, we'll be dealing with milli or microcoulombs. So just keep that in mind. Those are pretty large units, so we usually have smaller numbers. You can have an amp of charge, but boy, that's a lot of charge. You want to stay away from that because charge can harm you pretty major. Okay, so I wanted to get that in before we move to the nature of current. Okay, so here we have it. And this is what I was talking about before. Historically, this was often called the electrical fluid. Okay, and historically, no one understood what was moving and why it was moving. So the current was thought to be the flow of positive charge. That makes sense. Going from high potential to low potential. That made sense. In reality, it's a lot more complicated. It depends on the material, but unfortunately, most of the time in metals, which are most of your conductors, the current is the electron movement. Now, so therefore, even though what I said before, and I always tried to say conventional current, the conventional current is the one that goes from the high potential, which I can't find my pen now. Yuck, this is so aggravating. Okay. There it is. Every time I get it in place, that moves. Okay. Now, there it is. Here is your positive pole of your battery, your power supply. Conventional current moves from positive to negative, and that's why the conventional current is in that direction. However, because these wires are made mostly of metal, the actually electron flow is from negative to positive, and that's why the arrow is given that way, the electron current in that direction. Okay? In reality, don't get wound up with this, okay? Because the electrons really aren't moving that much. Now, also inside the battery here, it's really complicated. You have positive ions moving this way, negative ions moving this way. That's what makes this negative and that positive. So you have both moving in here, okay? Now, we're going to go back in a few minutes to the concepts of field. Okay, we've already talked about them. We're going to go back to them and you'll see everything changes with the field. Okay, so for now, conventional current goes from positive to negative. Electron currents from negative to positive. We're most of the time going to use conventional current, not electron current. Okay, so what are your current mechanisms? What actually makes current happen? Okay, we're moving toward page 150 or 6-11. How are we doing on time? Got to move along here. Your current mechanisms. Now, in liquids and gases, you have both positive and negative charges moving. Most of the time with liquids, you have ions. You have positive ions and negative ions, and they move in opposite direction. Okay? They're both moving opposite direction. Gases. A lot of time with gases, say that lightning strikes, and when it does, it moves charges around, and some go one way and some another because you have both positive and negative charges. Excess of electrons, deficit of electrons. Okay. But in metals, your delocalized electrons, those are the ones that move through a metal. So therefore, we sometimes will think of electricity as an electron gas. It's not always an electron gas, but a lot of times they think of it that way. Here is the deal. In reality, that movement of electrons is incredibly slow. Incredibly slow. And here's why. When there's no field applied, even to a conductor, which, oh, there it is, here, now this is even a good illustration, but we'll live with it. The electrons and the protons, the positive and negative charges are fairly evenly distributed in that wire. Let's just call it a wire, electric wire. If you set up an electric field, in other words, you have a positive on this end and a negative on this end. Nope, they got it backwards. I've got it backwards. A negative on this end and a positive on this end. Why did I say that? Because look at where the, oh, I'm sorry, no, I had it right. This was electric field, not electrons. Electric field goes from positive to negative. Remember, that's how the direction of the field goes. Well, if that's the case, the electrons are going to want to go toward the positive, and if you do have any positive movement, it wants to go toward negative. So your electrons are what are basically moving, so they go from here to that positive charge, to that one, to this one, to this one. Notice that is a very tortuous route. It's going from one to another to another. If it happens to hit another electron or get close to one, it could actually go backwards for a while because it's repelled by that electron. Then it turns around and comes back this way. Here it may be torn between these two, want to go this way rather than that way. The route is very tortuous. So actually, the actual move of electrons is incredibly slow. It's a slow drift of your actual movement of electrons. But you say, hey, it can't be that slow. If I turn off that light, it goes off. If I turn it on, it comes on. The wire is over here, the switch is, and that comes on almost immediately. So you say, hey, it's got to be fast. No, it isn't. It's the field that's fast. not the movement of electrons. Because guess what? In between this switch and that light, there's wires going up the wall, across the ceiling, down to the light bulb. The electrons moving there are incredibly slow. Okay? The field, though, is almost instantaneous. So what makes the light come on fast is not the electron motion, though that has something to do with it. It's the field that's been set up. Because all along that wire, remember, it's a good conductor, there's electrons all along the wire. As soon as that field hits, it's not these electrons that turn on the light, it's the ones right next to the light bulb here. They turn on the light because those start moving immediately right there as soon as the field goes into place. The field is almost instantaneous. The electrons are incredibly slow drifters. Okay. Now what makes this even worse is this is alternating current, meaning that all the electrons are doing are going back and forth, back and forth, back and forth. Okay, they're not really going anywhere at all. Okay, they just go back and forth, and they lose their energy to the light bulb as they go back and forth, back and forth. In what they call direct current, yeah, they're moving in one direction, but it's a very, very slow motion. Okay, so the drift velocity of the electrons is incredibly slow. The electric field moves through the medium at nearly the speed of light. That's why it's almost instantaneous for those to come on. And we're getting to what electric field is. It's change of electrical potential, electromagnetic potential, which travels at the speed of light. Okay. Now, here finally they show this thing. Your electric current, I knew it was in here somewhere, is your current, I. Why it's capital I don't know, but that's what the symbol for. Charge per unit time. The current is charge per unit time. The unit for current is amperes, named after Louis Ampere. The Q, the charge, is in coulombs, named after Charles Coulomb, and time is, of course, measured in seconds. So an ampere is a coulomb per second, or a coulomb is an amp second. Okay. Now, I was just mentioning the difference between direct current and alternating current. All of your formulas like this and others we'll get to all work whichever you're in, direct or alternating. The details of them may be slightly different, but basically they work the same. Okay? In a direct current, the charges move predominantly in one direction. Okay? Now back here, when we showed this, this was a direct current because it was a single electric field in one direction. The charges, yeah, they're not quite moving in one direction. They're zigzagging all over the place. Okay? But they're moving predominantly overall in one direction. Okay? In alternating current, the motion is oscillatory. It goes back and forth, back and forth, back and forth. The charges, net movement of the charge is zero. They're always moving, but just back and forth, back and forth, back and forth. There's no net flow, but we'll talk about it as if there is. They still talk about current, but it's not in one direction. It's back and forth, back and forth, back and forth. So there's no net flow, but we'll still talk about current in alternating circuits. In DC, direct currents, yeah, you can actually talk about the net rate of flow of those electrons. Okay. Now, where do we get these? Your electronic devices like this computer I'm working on, your telephone, this pad here, most of those devices are direct current. Anything that has a battery, direct current. Solar cells, direct current. A lot of things like this are direct current. Your automobile, it has a battery, direct current. Your alternating current, anything that you plug into the wall. Wait a minute, I thought you just said, isn't this computer plugged into the wall? Okay, I'm going to see if I can pull this up here. I think I can without unplugging something. Sure enough, the computer on this end is plugged into the, ultimately, I can't get it up high enough to show you. Well, it's attached to something else here. But anyway, I can't. Okay, it's plugged in ultimately to the wall through this cord. What in the world is this big old ugly box here? This part is plugged into the computer. Notice the difference in the wire. Big old thick wire, little bitty wire. Okay, what is this in between? I happen to feel of it, it's sort of warm. What this is an AC to DC converter. On this end, AC, that's what plugs into the wall. On this end, DC, that's what goes to the computer. So this is an AC DC converter. So that's why we can plug the computer into an alternating current and work. But we can unplug it there and it works off its battery until the battery runs down. Then we plug it in and recharge the battery again. So the computer is actually direct current, but it's being charged by alternating current. Now what's happening in here is, we'll talk about later in the chapter. Okay, so hang on to that thought. Okay, now let's see. Seemed like there was something else I was going to say about that, but let's move on. Now, the next concept we have here is the concept of resistance. Okay, and I think I sort of threw in the weasel word. Most of the time, the wires don't offer a lot of resistance. Now, I have messed something up here royally because I'm now. How did I do that? Okay, let me see if I can undo it. Picking up all this stuff. How in the world did that happen? Maybe that's how it happened. I'm just wrecking everything on my desk here. Okay, let's see if I can get it back now. No, I can't. My word. Okay. Let me see if I can figure out some way to untangle all this mess. I don't have time for this. Okay. Let's see if I can lower this back down without destroying everything. There, maybe I got it. Okay. Yeah, feels better. All right. In any wire, let's go back to this picture here. There is resistance in here. These charges do not move easily. So even though it's a good conducting wire, there's always a little bit of resistance. Of course, if that's a light bulb, you have even more resistance. If that's a stovetop on your stove or your element in your oven, your hot water heater, there's even more resistance. The clothes dryer, enormous amounts of resistance. Okay, so there are things that help, that keep things from moving well. Now, by the way, I should have hit this, and what I'm going to do now is just suggest to you. Here is a picture of a car. Usually the battery is in the front of the car, the brake light is in the back of the car, right? Well, if you were saying that when you hit the pedal, brake pedal about the middle, how long does it take the light to come on? Well, you sure hope it comes on instantaneously. But if you were to measure the movement of the charge, just like I said, the light switch here, it would take more than 5 hours for that electron to leave the brake pedal or leave the battery and make its way to the back of the car, the brake light. That wouldn't do you any good. It's not the electron moving, it's the field moving. As soon as you hit the brake, the field is set up throughout the whole circuit, and even though the electron will never, even though that's a direct current, will never get back there in time for anyone to see it, the field is there almost instantaneously. So the light comes on immediately. So that is an interesting little blurb. Please read that and make sure you understand it. All right, now what I'm talking about now is electrical resistance, and there is a mistake and misunderstanding, well worth a read, but let's move on because we really need to get this covered today. Now, because of all that opposition to the flow, oh wait, here's Dre here. Let me get Dre present. All right, we're building up a decent class size. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Got 10 students here now. Let's see if we still have 10 in the room, so to speak. Nope, we're down to 8. Okay, so that must have been some of those beeps we were hearing earlier. Okay, so Dre, we're in chapter 6, electricity. I like to call it electricity and magnetism, and we're right around page 151, which is 6-12, electrical resistance. Now, what electrical resistance is the basically what it's saying, the resistance of a material to allow electrons to move freely. Now, we talked about good conductors. No conductor, not many conductors are perfect. And what you have is loss of electron current energy. You don't lose electrons, you lose the energy of those electrons. Now there's two sources. One is collisions with other electrons in the circuit, in the current, because these are trying to move along. If they bounce into each other, one of them's bouncing backwards, one forward. But the other is collisions with other charges in the material. Okay, let's go back to, it won't go back, okay, to this. See, this electron here is being attracted to that positive charge, and then to this one, then to that one, and every time it bounces, it loses a little energy. Not a lot, but it loses a little bit. Okay, and if another electron happened to get in the way, like this one here, then it's probably going to deflect it and make it go around like this. Well, it lost a little more energy. Okay, so that's what we mean by electrical resistance. The loss of energy either by hitting other electrons, which makes a completely negative movement, or collisions with other charges in the material, which would be positive charges, and that would then they'll tend to attract and stick to them. Okay, the guy who did a lot of work with this was a guy named Ohm, a German physicist, Georg Ohm, and he studied electrical current and electrical voltage and found out there was a relationship between them, a direct relationship, and the constant of proportionality he called, well, that was the resistance. Okay, the higher the voltage, the higher the current, but they don't go up exactly with each other. The proportionality constant is a resistor. That resistor was later given the name of ohm. Now, we ran into a problem there, because most of the time we name, if you named it after somebody like Georg Ohm, you would give it the symbol. You named it ohm, you would give the symbol capital O. But what would be the problem with a capital O? Anyone have an idea? Let's say we had 5 ohms of resistance. What's wrong with that? It looks like a 50. You can't tell easily the difference between a capital O and a 0. Okay? So they, as they often do, went to the Greek alphabet. Okay? Remember, like when they had millis for a thousandth of a unit, milligram, millimeter, milli, anything. Well, they went and then went to micro. They couldn't use little m again, so they used the Greek symbol for micro, which is a mu. Well, when you go to the Greek alphabet, the letter that corresponds to our O is an omicron. Well, you have the same problem, except for the fact that in the Greek alphabet, there's actually two letters that both we start with the letter O. Omicron was one that follows nu, which follows our N, that's just like our N. But the other one is omega. Now, in the Greek alphabet, they don't have a Z, they have an omega. If you've ever heard the phrase alpha omega, alpha is the first letter in the Greek alphabet, and I can't find my pen. There it is. So I can't even think what the capital alpha looks like right now. I know the little alpha is like that, and it may be just a bigger one of those, but the capital omega is like that. So that's the symbol they use for an ohm. Capital omega in the Greek alphabet. One of the few units that has no bearing to a English unit, English number, English letter. That's the omega. That's where it comes from. Now, I wish I had time to tell the next dumb little story, but we're running out of time. Let's do Ohm's law. Like I said, it's the proportionality constant that relates voltage to current. Okay, and that's the ohm resistance. Now, this formula here you can write in two other ways. Here's one. If you divide both sides by R, then you get, these go out, I is equal to V over R. Okay? Or you could have divided both sides by I, and you get R is equal to V over I. So Ohm's law shows up in at least three different ways here. V is equal to IR, I is equal to V over R, R is equal to V over I. And I don't know if you recall back earlier, I mentioned to you that there were things, for instance, Navy schools always emphasize using either a triangle or a circle to help remember your relationships. And I wish I could find my pen. Okay, here it is. Okay, and this is the one I first heard it used in. Have a dividing line and a multiplication line. Put the thing that stands by itself, like V here, and this is I times R. If you're looking for voltage, cover the voltage, and you have I times R. That gives you this one. If you're looking for current, I is V over R. That gives you this one. And then the third one is, if you're looking for R, cover that up, and R is V over I. So that was the third one I listed here. R is equal to V over I. Now, that's just a mnemonic device to help you remember, but this is, it's pretty useful sometimes. Three different forms of Ohm's law. This is usually the one we think of, but this one here, but all three of them are forms of Ohm's law. Okay. So let's talk a little bit more about electrical resistance. Now, how are we doing on time? We've got about 15 minutes. Today's lab is based on Ohm's law, so get that one down. Tuesday's lab will be based on this one, okay? They're very similar, one slide apart from each other. This is more about resistance, okay? What is it that makes up resistance? What are the parameters? What are the features of a material that contributes to resistance? One feature, okay, the resistance factor here, let me make sure I haven't skipped something here. I don't think I have. Okay. One feature that will determine resistance is the type of material. Now, I've sort of been talking around this a little bit, but it's certainly here. Remember, different materials have different amounts of heat conductivity and different materials have different amounts of electrical conductivity, and basically they're almost equivalent to each other. Silver is the best heat conductor, it's the best um, electrical conductor. Copper is next in both areas. Um, Gold is pretty far up there in both areas. Iron is not as far up there in both areas. Aluminum is between gold and iron. So they all have their hierarchy here. So the type of material certainly makes a difference. Okay. Now remember I said the stovetop or the element that's in your oven. It's also in your hot water heaters and things like that. Those are very high resistant materials, metals. The material is usually called nicron, I think it is. It's a mixture of nickel and chromium. Very high resistance, therefore it heats up really quickly. So the type of material certainly makes a difference. Also, the length of material makes a difference. Okay? The longer the piece of material is, the more resistance you have, because the more collisions you have in between. Okay? Another feature is the cross-sectional area. Why is that important? The smaller the cross-sectional area, the more resistance you have. The bigger you have, there's more place for the current to flow. So cross-sectional area is an inverse relationship. Temperature also matters. Okay? The higher the temperature, the more resistance you have. Now let's think how these affect something very common to us. We've mentioned several times an incandescent light bulb. And y'all are all old enough that you remember incandescent light bulbs. Maybe today in your home you have mostly compact fluorescents or LEDs, but at some point in your life I bet you had mostly incandescent light bulbs. And if you think of that filament that's in the light bulb, what's happening in that filament and what makes that light come on is that filament has high resistance, and therefore it gets hot very quickly. And when it gets hot, it glows. And who developed the light bulb was Thomas Edison, the one that we know and love. Okay, it took him a long time and an enormous amount of effort to come up with the best material to put in that filament. What he chose was tungsten. After many tries, he found out that tungsten worked quite well. It had high resistance. Because of the nature of the material, tungsten had higher resistance, say, than the copper that got the electricity to the light bulb. Tungsten had a lot more resistance. But if you've ever looked at one of those clear light bulbs, if you've ever seen one of those, and look at that filament, you'll see that filament is in a very tight spiral, and maybe 3 poles on that spiral or something like that. Okay? What that spiral is doing is making that length of material way longer. So the longer length of material is also increases the resistance. The cross-sectional area, think of that. That filament in there is about the same thickness of a hair. I don't have much hair to show you, but that would be the thickness of a hair. It's incredibly small cross-sectional area, where the wire leading up to that light bulb is a big old thing, you know, not that big, but it's much bigger than the thickness of a hair. So the cross-sectional area has been reduced in that filament as well. So the length, the type of material, tungsten versus copper, the length of material, that coil that makes it a very long length as opposed to just that short distance in there, and the cross-sectional area where it went in as a pretty good size wire. I'm trying to think of something here. I bet you that wire coming in would be bigger than the tooth of this comb, and the wire that's in that filament would be like a hair. I mean, so it's incredibly different. Okay, I think it's even bigger than the tooth of a comb. Okay, and the cross-sectional area is, yeah, that's what I was just saying. Now let's think about this too. Have you ever had a light bulb blow on you. It went out. The filament broke. Have you ever had that happen to you? Anybody? I have many times. I bet you some of you have too. You're just too shy to speak. Okay? Aren't you? Okay? When did that light bulb usually blow out? Most of the time for me, when I first turn it on. Very seldom have I been sitting in a room and the light bulb goes. It's happened, yeah. But most of the time it's when I first turn it on, pop, it goes. Why is that? Because the temperature of that filament is very low when I first turn it on. Okay? And because the temperature is low, that means the resistance is low as well. The higher the temperature, the more the resistance. So if it's a very low temperature, very little resistance, you have a surge of current going through that. And if that wire is weak, if you've been using it for years and years and years or something like that, and the wire is a little bit weak and it gets a surge because the temperature is low, the resistance is low, that's when it breaks the wire. Okay? Whereas right now, this is not a incandescent bulb, this is a LED, but right now, very unlikely that bulb would ever go out, even if it was incandescent. When I come in the morning and turn it on the first time, that's the time it's most likely to blow. So temperature also is a resistance factor. Now, while we're on the subject, there are materials called superconductors. Now, like we just said, when the temperature is low, oh, I'm on the wrong pad. Temperature is low, the resistance is very low as well. If you drop the temperature down close to absolute zero, in some materials, and the funny thing is it's not the same materials you would expect, the good conductors at normal temperatures are not necessarily superconductors at low temperatures. It's other really strange materials make your superconductors. But the negligible resistance when the temperature is very, very low. And these form what they call superconductors. Basically, your resistance almost goes to zero. And there have been a lot of Nobel Prizes in physics awarded on the study of superconductivity. Okay, there are not very many practical applications of it, though there are some, because your resistance is very low. That forms, and we'll talk about this later, your conductance is very high, and when you have very high conductance, you usually have a great flow of electricity, and the flow of electricity is what creates a magnetic field, and the magnets that are formed when you're using superconductors are incredibly strong magnets. And in Japan, they have some rail lines that go at very high rates of speed because the conducting wire is a superconductor, and that lifts the plane, the train, the rail car off the wire, and there's almost no resistance there at all. I'm talking about frictional resistance because they're never touching or very seldom touching. So there are some practical applications of it, but the downside is it takes a lot of energy to create those very low temperatures because you're having to drop the temperature down to close to absolute zero. Not there, but close to it. So that's illustrated here. How are we doing on time? Okay, let's see where else we go from here. The next topic, next topic is electrical power and work. We're going to start there next time. Let's see if we can get examples 6.3 and 6.4 done. Okay, so let me see if I can find a good place to do this. I can't seem to find a good place, so let me go back to this slide and go to my whiteboard. Most of the time I find room on the slides to do it, but let's go to the whiteboard. First time I've used it today, so I need to move things around. Let me try to do this quickly and this quickly. Okay, you probably can't tell I'm doing anything, but I am moving my whiteboard around so it gives me more room. A light bulb in a 120 volt circuit. So the first thing they give you here, if I could find, oh, there's my pen, 120 volt circuit. Well, that's obviously your voltage. Remember, this is the one thing that the unit is the same as the symbol, capital V for voltage and volt, potential difference, okay, is switched on, and the current of 0.50 amps. So 0.50 amps, that is your current, and the symbol for current is I. Okay, flows through the filament. What is the resistance of the bulb? So we're looking for resistance, and this is very timely. We're doing this now. What's the formula for resistance? Does anyone remember? It's Ohm's law. V is equal to IR, or IR is equal to V over I. So this would be 120 volts divided by 0.50 amps, and this is going to give you something in ohms. So if I can find what in the world I did with my calculator. Here it is. Okay. Got 1 minute, so let's see if we can do this quickly. Go to the calculator. Don't need scientific notation here. All you need is your regular calculator. That's 120 volts divided by 0.5 amps, and that will be 240 ohms. Okay, and that's exactly what they've got in the book. 6.4, what current? This time we're looking for current. So this is the unknown here, is the current. What current would flow through an electrical device in a circuit with a potential difference of 120 volts? Well, potential difference again is voltage, and that is the same symbol as 120 volts. And by the way, folks, when you see problems that list 120 volts, think AC. You don't have to know that, but you never have batteries with 120 volts. I mean, that's just way too hot. That would be your AC circuits. And a resistance of 30 ohms. So here's your resistance of 30 ohms. Okay, well, what is current? Ohm's law. There's 3 different ways you could write it. Okay, and on the current side, that would be voltage divided by resistance, which would be 120 volts divided by 30 ohms. And here you can just divide out the zeros there, and 12 divided by 3 would be 4. What do we measure current in? Amps. Okay, 4 amps of current. Now that, folks, is a lot of current. Okay, a whole lot of current. So don't ever play around with any 4 amp currents. This is more reasonable. 0.5 amps, half an amp, that's more reasonable. 4 amps, that's a lot of current. 240 ohm resistance, that's pretty common. 30 ohm resistance, that's pretty low resistance. That's why you have so much current there. Okay, so that's finished that. And I think we're probably out of time, aren't we? So we'll begin next time with electrical power and electrical work. So we'll begin right there on page 152. Okay, let me put my paper in place, and if it's okay with you, I would love a break. Okay, are y'all in favor? Break. Okay, we are recording again. Let me just check and see if anyone else is in the waiting room. Doesn't look like it. Valerie, I know, was going to try to be here by 5:45, but her work was tying her up, so she must not be back yet. Okay, we have 8 students here. We have had up to 1, 2, 3, 4, 5, 6, 7, 8, 9, up to 10, so we're missing one that we had earlier. All right, so let's go for the lab. Okay, now where I'm going to go is here. Thomas, I was in the process of doing an email for you. I didn't get it finished. I just ran out of time, so I'll get that back to you in a bit. Okay, I'm going to get out of that for now. Get out of messages for now. You can't see this. Get back into the class for now and go to a new share here, which of course is here, Google Chrome. And let's go down to the weekly. Now, this is really awkward. I'm going to move y'all up here to the top. You can't see what I'm doing, but oh, did someone else try to come in? Maybe I just left this open. I don't see anybody else trying to come in. So let me go down here. You can see my Blackboard, right? I'm going to open weekly assignments.
Yes.
Okay. And we're in week, what are we, week 6 now? I believe that's right. Okay, let me make sure if that's right. Nope, it must be week 5. Okay. Yep, I think that's it. Okay. Yep, there we are. Now, these look like they're same labs, but there is your place we're going, same place we've been just about every time. The simulations from the University of Colorado. It's physics educational something or another from colorado.edu. This is the one we did last time. I finally got it worked up, so if you have it, if you want to have a template to put it in, you can use that. If you've already submitted it or already working on it, or use the one that Valerie sent out or whatever, you can use that. But if you want the one that I was working on, that it. Now, the last time I taught the course, the lab we're doing today was Lab 8. Now it's Lab 9, but I didn't change the name of it. So that's what we're going to have, but I already have it open. So what I'm going to do here, I will open my simulation here. I'm going to move y'all back down to the side again. And we're going to physics simulations. And we're going down to Ohm's law. Okay, which is just what we got to in class today. Okay, and because it's alphabetical, it'll be quite a ways down here. Okay, getting closer. Getting close. Oops, there it was, right there. Okay. And how you get it open is click on the triangle inside the circle. So there it is. Takes a few minutes to open. Now, what we're going to do next, let me pull open my slide. Okay. That's not the right one. Okay, let's, where did that one come from? Okay. Okay, why that one's open, I'm not sure. So let me go back to this. Why won't, I'm going to have to close this. Okay. That's not the one I want. Okay, there is the simulator. Let me see if for some reason I had it open before class and now it's not there. So let me go and get it open again. When you have too many things open in this system, it just falls apart. Blackboard is awkward. PowerPoint is awkward. Everything is awkward. Okay, I've got to move y'all out of the way again, so sorry about this. Let's scroll down till we get to here we are. Okay, Physical Science 112, and we're in Lab 8. Now this isn't we're in Lab 9, and when I open it up, I think you'll see that. There it is. Okay. The title of it is L8, but it's really Lab 9. There it is. All right. Are y'all all together now? Do any of you need some time opening things, printing things, or anything else? I don't want to go too fast, but I don't want to waste your time either. Are you okay? Can you see my slide?
Yes,
okay.
sir, we can see it.
Okay, good deal. So this is Ohm's Law, Physical Science 112, Ohm's Law. I don't know why those are written together. They shouldn't be. Lab 9, and be sure you put your name when you turn it in. Okay, I've abbreviated this somewhat. Go to the Blackboard page for this course. You know, we were just there. Go to course content. That's where it opened up with. Go to week 5. There I have it correct here. Scroll to instructional materials under week 5. Click on laboratory simulation link. We did that to get there. And click on simulations and then on physics. We've done that. Scroll down to Ohm's Law and click on it. We've done that. And click on the start button and the triangle in the gray area circle. We got that one. When it comes up, note that the 3 batteries in the series add together. Now we haven't done that in class, but that's what's happening. So that's why I wanted to show you this first. Let's now go to the simulation. I think that's right here. Yep. All right. Here are your 3 batteries, 1.5 volts, 1.5 volts, 1.5 volts. 3 of them add together. Okay, that's because it's this one to that one to that one there, head to tail, head to tail, head to tail. That's called a series connection. We haven't hit that yet, but that's what it is. They add together, so what does 1.5 plus 1.5 plus 1.5 add to? Anybody? 1.5 plus 1.5 plus 1.5.
1.5, 1, 2, 3, 4.5.
4.5, exactly. Okay. Now they tell you here, so that's what, oh, wait. I thought this was showing. It's not showing. Why in the world was that not showing? Okay, can you see it now? 1.5 plus 1.5 plus 1.5 is 4.5, which actually shows up over here as well, okay? Now, they tell you, okay, so that was the first question here. Let's go back to our lab. So they add together, what's their total voltage? 1.5 volts. Now, I have way too much line there, but I wasn't going to go back and change on that. Says note and record the indicated current. So let's go back to our slab here, our simulation. Where slab came from, I don't know. Okay, there it is. They gave you 9.0 milliamps. Now remember what milli stands for? 1/1000ths. So this, and I don't think I can write on this slide, but this is 9.0 times 10 to the minus 3. That's what milli stands for. Okay? Now, this is a very small current, and that's, they put a very small I there, okay, which is interesting. Okay? So if you know the current is 9.0 milliamps, it says calculate the voltage. And you know Ohm's law is R is equal to V over I. So with your calculator, and for some reason I have completely lost my calculator. That's what I've been looking for the last few minutes here. It was just here. There it is. Okay. Sorry about that. It's black in the shadows. Okay. So I'm going to turn on my calculator, which is my phone. Okay. All right. Now, voltage is equal to, or current is equal, I'm sorry, resistance is equal to V divided by I. Just divide both sides by I. V over I is equal to R. Okay? So if you take your 4.5 divided by 9, oops, I do have to have it sideways because I have to have scientific notation. 9 EE negative 3. So I have to type my 3 first, then change signs, make it negative, then hit equal. What do you get as your resistor? Why can't I see this? There it is. 500 ohms. And look at what this is, 500 ohms. I wish I could get one of these things to disappear, but it doesn't. Everything shows up here. I kind of hate that, okay? But we're stuck with it. This is Ohm's Law Lab. All right, so let's go back to the lab. Everybody got that so far?
I got it.
Okay. So here we had 4.5 volts. The indicator current was 9 milliamps, or you could have put 9.0 times 10 to the minus 3 amps. And then when you divide the volts by that current, you get the 500 ohm resistor. Okay. Now, use the voltage adjuster in the right rectangle to choose 5 different voltages with your same 500 ohm resistance. Okay. And then we're going to calculate the currents that should result. You've got to show your work. You can't just write down what's on the page. You've got to show your work. So you can, if you need to, if you print it off your page, flip it over and write on the back of the page. If you're doing this on notebook paper, show your work. Okay? And fill in the table. So do you want to choose your voltages now? You can if you want to, or we can make them up as we go. Now remember, those batteries were each showing as 1.5 volts. So you could do 1.5 volts, 3 volts. We already did 4.5. You could do 6 volts and 7.5. Do you want to do that, or do you want to do 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, or 2 volts, 4 volts, 6 volts, 8 volts, 10 volts? Whatever you want to do, how do you want to do it? Do you want to choose your voltage? You tell me. Somebody.
I'll just do it together. We'll do 1.53 volts and the rest.
Okay. I heard so many things I can't distinguish. Did anyone come to any consensus there? What voltage you want to use first?
1.5.
1.5. So you want to use 1.5, then use 3, skip 4.5 and do 6. Do 6 here, then do 7.5 and 9. You want to do that? 1.5, 3, 6, 7.5, and 9. Y'all okay with that?
Yes.
Okay, fill in your table there. Either on a scratch piece of paper, if you've already printed it off, fill it in. Okay, it says use the 500 ohm resistor. So all these resistors are going to be 500, 500, 500, 500, and 500, right? Keep that resistance the same. Got it? So the voltages are 1.5, 3, 6, 7.5, and 9. The resistances are 500, 500, 500, 500, and 500. Got it? The voltages or resistances? Voltage. 1.5, 3, 6, 7.5, and 9. We skipped the 4.5 because that's the one we started with. Okay, is someone talking to me or is that background noise? Okay. Have y'all got it down? You got the voltages, you got the resistance. Okay, so let's take that first one, 1.5 volts. So it's going to be 1.5, okay, divided by, now your resistance, remember these were in ohms, so it's 500 ohms, 500. I hope I put my division sign in there, then press equal. And what do you get? What's your calculated current?
3 M8.
Okay, okay, are you looking at the simulation or did you calculate it yourself? You can be honest. That is 3 milliamps, meaning 10 to the minus 3 amps. 3 milliamps, which is exactly what that is, 3 times 10 to the minus 3. Okay, let's do the next one. That would be 3 volts, wasn't that your next voltage, divided by your 500 ohms, 500 ohms, equal, what did you get? Anybody?
6 milli.
6 milliamps, exactly. Okay, then let's go to, what was the next one? We were going to skip 4.5 and go to 6. So 6 volts divided by 500 ohms equal, what you get?
12 milliamps.
12 milliamps, excellent. And then we were going to do 7.5 volts divided by 500 ohms, and that gave us how much?
15 milliamps.
15 milliamps, excellent. And then the last one I believe was 9 volts divided by 500 ohms, and that gave us what?
18 milliamps.
18 milliamps, okay? That's what we calculated. Hopefully you're filling in a table much like this one. Even if you don't have this very table, you can do it. So let's go to our screen share and see if that agrees with what you got here. Okay, so let's lower our voltage here for that first one to get down to, wow, I didn't know it had sound with it, 1.5 volts. When I did it earlier, I didn't have on my headset, so I didn't know it had sound.
Oh, yes. Alien spaceship sounds.
Yes, it was, wasn't it? 1.5 volts at 500 ohms gave us 3.0 milliamps. Now, why 3.0? We're assuming two significant digits here. You can't assume two significant digits there, but I guess you have to assume because it's not indicated. 500 ohms, that would be 3.0 milliamps. Did your calculation agree with this? Yay or nay?
Yes.
Okay, good deal. Let's move up to 3 volts. There we go. That would be 2 dry cell batteries. Did you have 6 milliamps?
Yes, sir.
Okay, so that agreed also. Then I think we went to 6 volts, didn't we?
Yes, 6.
And did you get 12 milliamps? 12.0 milliamps when you did your calculation? Yay or nay? All right, yay, we got it right. Then let's go here to 7.5 milliamps. I hope we can get there.
15.
15.0 milliamps. Excellent. And then the last one we did was 9 volts.
18.
Oh, we just made it. And that, sure enough, was 18.0 milliamps. Did that make sense? Yay or nay? Okay. Is this helping you understand Ohm's law?
Yes, sir.
Excellent. Okay. You don't have to answer that way, but that was a good answer. Okay. Now, what we do next here, it says use the resistance adjuster in the right rectangle to choose 5 different resistances with, go back to your 4.5 voltage and calculate the currents that should result. You must show your work, fill in the table below, and then we'll see if the calculated values match the indicated currents. Okay? This shouldn't be currents here. Yeah, it would be. Okay, that's right. So, I think I've got something wrong here, don't I? I do. Use the resistance adjuster to, oh no, we're okay, we're okay. So we're going to have 4.5 volts in all 5 of these blanks, right? 4.5 volts here, 4.5 volts here, 4.5 volts here, 4.5 volts here, and 4.5 volts here, right? That's what it says. Use that same 4.5 volts in all 5 of those voltages. Now, we need different resistances. Now, what we had before was 500. So you want to do 300, 400, 600. Let's see, let's not go that way. Let's do 200, 300, 400, 600, 700. Are y'all okay with that? Or y'all can choose anything else you want. But we have to keep something that's going to show up on our resistor things. Are those okay with you?
Yes, sir. So we have 200, 400.
Wait, no, okay. No, 200, 300, 400. Skip 5, we've already done that. 600, 700. So 200, 300, 400, 600, and 700. Now, if y'all want to choose different ones, you can. Fill out your tables however you got it, and then see what you get. But are y'all okay doing it that way together here? Yay or nay?
Yay. Yes, sir.
Okay. Then how do you calculate your current? What does Ohm's law tell you?
4.5 divided by 200.
That's it exactly. What do you get? 4.5 divided by 200. 4.5 divided by 200. 22.5 milliamps. That's absolutely correct. Okay. Yeah.
2.25 million.
Okay. 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 I'm hearing a lot of talking. That did come down to 22.5 milliamps. If I can get it to show up. To move your decimal to get milliamps, you move your decimal 3 places to the right. 22.5 milliamps. Okay. What was the next resistor? It was still 4.5 volts divided by, was the next one 300? 300 ohms. That gives you what? Anybody?
Let me get my calculator out.
Yeah, I'll do that. Say again?
For 300?
Yeah, what did you get as your calculated current?
15 millivolts.
15 milliamps. Yeah, 15 milliamps. Perfect. Everybody got it? Now, if y'all want to use different resistances, you can. Okay. Again, we're using the same current, 4.5 volts. Divide that by, what was the next one? 400, wasn't it? Okay. 400 ohm resistance. Okay. And what did that?
25 milliamps.
Okay. 11.25 milliamps. Does everybody see that? You can't move your decimal 3 places. 11.25.
You said 11.25, right?
That's correct. You move your decimal 3 places to the right, and that gives you 11.25 milliamps. Okay? How are y'all doing? Okay?
Yes, sir.
All right. Now we were skipping 500, so we go to 600. So it's your 4.5 volts divided by 600 ohms.
75 milliamps.
Not 75. 7.5 milliamps. You're absolutely right. 7.5. Move your decimal 3 places to the right. The higher the resistance, the lower the current. Right?
Yes, sir.
Everybody got it so far? Okay. And I think our last one was 700. Is that right? 700. No, I'm sorry. 4.5. You start with the voltage. 4.5 divided by 700. And what did you get? 6.2. Let's make that 6.43. Okay. Round it up because the next digit's 8. You don't need to carry all those digits around. 6.43, approximately 6.43 milliamps. Okay. Let's go back to our simulator. Okay. And we were going to go back the voltage, take that back to 4.5. Okay. And we're going to start our resistor. Where do we start that? At 200?
Yes, 200.
I may not be able to hit 200 on the nose. I can't quite get 200. Let's see if I can get 199. Okay, I'll go with 202. We won't be exact, but we'll be close. Okay? What did you get as your current?
22.5.
Okay, and we got, and I'm not on the money, so 22.5 looks like a good answer, doesn't it?
Yes, sir.
Okay. Everybody okay with that? Okay. Let's move it up to 300 ohms. Oh, look at that.
Right on 15.
Yeah. And did we get it? Is that what we calculated?
Yes, sir.
Excellent. Excellent. Everybody got that one?
Yep.
Okay. Next was 400 ohms. I can't seem to land
My
on.
husband worked the overnight shift, so that's him you hear in the background. I'm sorry.
Okay, no problem. I'm not hearing anything but all the noises. Okay, the ding 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 ding, yeah, the spaceship noises. I can't get 400 on the nose. This gave us 11.3. What do we get?
11.25.
I would say that's close enough, wouldn't you? Okay, so we'll say we agree. Okay, I think we go next to 400. 600 ohms, don't we? 600. Okay. I can't get 600 on the nose, but I can get 601. If y'all can do better than me, go for it, folks.
Well, it's crazy we got the answer of 7.5 though.
Yeah, well, that's because you see, this is only two significant. Yeah, this is 3 digits. That's only two, so it's not at all surprising. We're within two significant digits. If you round this to two significant digits, that would be 600. Okay, so yeah, it's not at all surprising. Okay, how about the next one was 700, wasn't it?
Yes.
Let's see if we can get to 700. I'm not very good at this. That's about as close as I can get.
And we had 6.43.
That looks like about the same. Say they round to only two significant digits. We were rounding to three. So yeah, that rounds to the same thing. Does this make sense?
Yes, sir.
Yeah. Because mine I still have up there, 6.4 would be about the same value. Okay? We said 6.43, but 6.4 would do. Does that help with Ohm's law?
Oh yeah.
Okay.
Yes, it does.
Okay. Now y'all can play with this to your heart's content but I think that's all I had on my page. I did this last spring and I was just basically learning to use these simulators back then. Yes, what is it?
For match, is that we're supposed to put yes or no if we got close or not?
Yes, yeah, if it was close or not, that's what you put. Let's go back to this. Does it match? Do the calculated values match the values from the simulation? So we calculated first, then you wrote down from the simulator what your indicated current was, and then did those match. Yeah, so it's yes or no. And I think that's all we wrote. Sorry about that, folks. This is too short a lab. We should have done some more, don't you think?
Nah.
That was easy, wasn't it? Okay. Now, my only regret ending early is that Valerie hasn't made it in yet, but she must have had to work late tonight. So hopefully she'll be able to pick this up from the PowerPoint, from the YouTube video. Okay. Any questions? You want to play around some more or try some different um, deals with it? Because you have, let's see if we have other options. No, I guess I don't think we're allowed to change the current. So all we were allowed to change was voltage and resistors. Okay. So any questions? Anything else you want to Me to enter different voltages or enter different resistances? Anything you want. Anything?
No, sir.
Okay. So you want to call it quits or any
Yes,
more
please.
questions? Okay. So I'll go on and stop the sharing then. And unless there's some additional questions, it looks like we've already lost a few people, I'll end the recording. Now, folks, I don't know what the weekend's going to be like, but my wife's an epidemiologist, infectious disease epidemiologist. She said the counts, we're setting new records almost every day. I don't know if we are in Alabama, but we certainly are in the U.S. So, folks, please be safe. Please be safe. Now, some of you weren't here at the very beginning. Um, if you have not registered for spring term yet, if there's any way possible for you to uh, sign up for virtual advising tonight and get your advising done tomorrow, then please try to get registered for spring term tomorrow. If you can't, or if you have questions, next week on both campuses, Bessemer and Birmingham, they're going to be holding really big registration events. Now, the disadvantage is you got all those people in a close proximity. Everybody's going to be masked. They're going to have plexiglass between you and the instructors, that kind of stuff, but still it's dangerous. If you can, do it virtually. If you can't, go to campus next week, sometime between Monday and Thursday, between 9 in the morning and 7 in the evening, and get your registration completed. Please, please try to do that. Another thing that came up this past week, Mr. Matthew West, who teaches sociology and history, is working on his doctorate at University of Alabama. He's in a statistics class. They had to come up with a project so they can collect data, measure data, and analyze data. And he asked me to put that out there for all the students. So if you go under Blackboard announcements, you'll find that one as well. So if you can, please do that as well. Okay? Any final questions or issues or concerns or problems? Let me say again, on the Birmingham campus, it's going to be in the Academic Success Center next week. That's that big new building on Wilson Road where Winona Elementary used to be. Okay? On the Bessemer campus, it's going to be in the Ethel Hall Auditorium. Now, there is an Ethel Hall building on the Birmingham East campus. It's not there. This is on the Bessemer campus, Ethel Hall Auditorium. They'll have it set up, nice spacing, plexiglass between advisee and advisor. All that's going on. Everybody wear masks. Be sure you take a mask with you. If you don't, they'll probably have some, but you've got to have your mask on, worn properly. Please, if you're going to go to campus next week, be careful. Okay? Any questions? Okay. I'm going to end the meeting for everybody, so y'all have a safe weekend and be careful registering next week if you do go to campus. Okay? Take care, people. We'll see you on Tuesday. Okay? Bye-bye.